Hi, I'm Bruce, and welcome once again to my Rocky Mountain Lab. And what I'm going to talk about today is a project I'm involved in. And it revolves around this General Radio 1840A output power meter. This is a very well-built, heavy-duty 0 to 20 amp, or 20 watt, power meter. It is adjustable for a series of impedance loads. So, like I could monitor the output from an impedance of zero point 0.6 ohms up to 128 ohms, or 150 ohms up to 32,000 ohms. So I can adapt this unit to a great many impedances, and then I can measure 2 milliwatts, 20 milliwatts, 200 milliwatts, 2 watts, or 20 watts of switch selectable power. So if I'm in the process of building a small amplifier and I want to know what power output I can expect out of that, and read it, then I can hook it up to this, adjust the impedance, and then we're off. Okay, right now I've got it connected up to that Ray Caldana 20 megahertz log linear sweep generator up on the top up there. And that's a 50 ohm output, so I've put myself on ohms. I've dialed into 50, and I've got myself right now on the 200 milliwatt scale, and at the moment I am reading 200 milliwatts of output. You can see I'm pinned over there. If I pull this thing off, you can see it fall. So anyway, I think it's a very handy device to have on a bench for monitoring the power capabilities of your circuits and so on. The one negative thing, though, is that it's only 0 to 20 watts. And a lot of amplifiers out there today that I might like to test would be 100 watts or more. And General Radio addresses that in their manual for this unit. What they suggest is that I build a T attenuator, whereby almost exactly 90% of the power that's fed to this unit for measurement, 90% of it bypasses the unit and goes through resistive elements, and the other 10% is measured on the unit. Well, in that way, I could measure up to 200 watts of power on a 20 watt machine here. So I wanted to do that, and that's what this whole exercise is going to be about, is how I'm going about doing that. I did find a line of resistors, 100 watt precision 1% resistors, power resistors, available from China. It's almost impossible to be able to, in 3 resistors like the T attenuator would be, to buy the resistances you would need exactly. But my hope was I can approximate those resistances by coupling 1 or 2 or 3 of those resistors that I can find online together to make them. So let's just go through that whole exercise and see how we do. Okay, so we can see the attenuator here is made up of 3 resistors, 2 of which are equivalent to 0.5195 times the impedance Z. Choosing Z to be 8 ohms, we're going to wind up with 2 resistors at 4.155 ohms, each needing to be 134 watts, and the third resistor is 5.6216 ohms at 66 watts. Odd values, but maybe we can make them, huh? So at the left side of the screen, you can see a selection of 100 watt resistances that I was able to find online on eBay. And I found, after studying that list, that if I was to use a 3.9 ohm resistor in series with a 0.25 ohm, I could get 4.15, which is relatively close. And if I chose to use a 5.6 ohm resistor and put a 2.01 ohms in series with them, then I could get 5.62 ohms. So then my question was, would those be acceptable in terms of error to the design? Well, when I received the resistors that I had ordered, I found that the values differed a little bit more. But I could, after making a 4-wire measurement of the resistance values, I found that I could take two resistors and I could have 3.945 ohms in series with 0.243 and come up with 4.188, and that would be one of my resistors I needed. Another was 4.039. If I hooked that up with a 0.240 ohm, I got 4.279 ohms, which again is relatively close. And then the third resistor I measured was 5.637, which meant that I didn't need the 0.01 ohm resistors at all. Looking at figure 1, you can see that all of the power for the circuit runs through R1, and it branches out to R2 and R3. And if we expand R1, R2, and R3 to include the resistors that make them up that I purchased, we call those RB, RA, RB, RD, RE, and RC, and so on, as in the drawing here. Then my RA, which is 3.69 ohms, I believe, it was, if it's carrying the largest amount of power, then we should calculate, it'll be the limiting factor, and we'll calculate what the power is through RA. The resistors I purchased could only handle 100 watts. If the power in resistor A is at 100 watts maximum, and it's got a 3.945 ohm value, then the current through it must be equal to the square root of 100 divided by 3.945, which is 5.035 amps. The voltage on R1, V equals IR, must be equal to 5.035 times 4.188 ohms total, which would give us the input voltage at 21.085 volts across R1. The total power dissipated by R1 is therefore P equals IV is 5.035 times 21.083, which would give us 105.16 watts. So you got to remember that RB is part of R1, and then it dissipates the extra 6 watts. Looking for the total resistance of the T attenuator here, we can see that R2 is comprised of the series combination of RD and E, which was 4.039 and 0.24 ohms, giving us 4.279 ohms for R2. But that resistor is also in series with the load, which is in this case 8 ohms, and therefore the total resistance of that arm is 12.279 ohms. But that 12.279 ohms is in parallel with R3, which is 5.637, and together they wind up giving you 3.853 ohms for the equivalent parallel circuit. So if you add R1 to that 3.853, you're going to wind up then having the total circuit resistance, which is 8.051 ohms. The current flowing through R1 must also flow through the combination of R2 and R3, the parallel combination. We just got through saying that that equals an equivalent 3.863 ohms. The voltage drop on that 3.863 ohms then must be equal to 5.035 amps times 3.863 ohms, which is 19.451 volts. But you add that voltage drop to the voltage drop that we had across R1, we calculated earlier, that was 21.085. You add those together and you get 40.536 volts at the input. Knowing that I now have 40.536 volts at the input and I had a current of 5.035 amps, that means I must have a wattage input of 204.091 watts maximum when RA winds up exceeding its 100-watt rating. So let's figure out what power would be provided the 8 ohm output when we have 204.091 watts at the input. So earlier we calculated that in R1 we dissipate 106.16 watts. And if we're inputting 204.091 maximum, then we could subtract that 106.16 and get the remaining circuit wattage of 97.932. And that would be the parallel part of the circuit. But that has 3.863 ohms. And we know that the total current in the circuit is 5.035 amps. So therefore the voltage on the parallel part of the circuit must be equal to V equals IR, which would then be 19.449 volts. The voltage is the same on both halves of the parallel circuit. So current flowing through R3 can be found as current equals voltage over resistance, which would be 19.449 volts divided by 5.637, which gives me 3.45 amps. And the power on R3 must then be equal to 67.099 watts. So knowing that I had 97.932 watts total on the parallel circuit, and that I got 67.099 watts in the left-hand side of that parallel circuit, that means that 30.833 watts are dissipated in the right-hand side. The equivalent resistance of the right-hand side we found to be 12.279 ohms. So the power dissipated in that branch has to be 30.833 watts. Then the current flow through that branch is equal to I equals P over R, the square root of it, which gives me 1.585 amps. Knowing this, you can then calculate that the power dissipated on R2 is 10.75 watts. This must mean that the 8 ohm load dissipates 30.833 watts minus 10.75, leaving me a total of 20.083 watts. So 204.091 watts in delivered 20.083 watts out. That's a power ratio of 0.0984 instead of 0.1. 0.1 would have been perfect. So 200 watts in would give me 19.68 watts out to the meter instead of the desired 20. That's less than a 2% error. That's not bad, and I can live with that. And when I did the calculations for the second part of the circuit using those resistors, I actually got an error of 0.554, so I'm going to be quite happy. Okay, well, I'm giving you a look at making the case cabinet, or what do you want to call it, for this T attenuator that's going to be used with my audio power meter. And I looked through my stack of stuff and I ran across this RCA WR515A. It was a chroma bar generator back before the digital TVs kind of took over. Kind of useless now. I don't even know if anybody has any of these anymore. As far as TVs. But these units are selling cheap because nobody wants them. The reason I picked it up is I looked at the cabinet and I thought, you know, it has possibilities. And once I got it, I realized I made a good choice. I've only got it sort of kludged together right now because I'm going to easily take it apart. Came with a nice handle, nice extruded aluminum front panel. Now I'm going to take this plate off, and you can see that I've done some saw cutting here. Cut this rectangle out. What I'm going to do is I'm going to get some perforated sheet metal, and I'm going to put that perforated sheet metal behind this and screw it on. And that will allow a flow of air from the back to the front. And in the back of the unit, I'm going to mount a couple of fans. And that will blow air through the unit. And let's keep going. I'm going to take this faceplate off. You can get an idea here. It's fairly thick. I'd say 1/8 of an inch. I had a problem cutting it. I tried really hard to do a very nice job, and I got right to this middle spot here, and it started going crazy on me. The blade started sticking and pulling up the unit. I'm going to have to try and file that down a little. However, not to be deterred, let's take off this handle. All right. We'll take this cover off. That exposes this internal plate, which has a well depressed in it. I don't have any use for the well, because what I want to do is I want to mount groups of these resistors up on the top here and screw them down to a plate. There'll be 2 rows of 5. There'll be another row of 5 over here. And so I want the plate to be flat so that I can have nice thermal conductivity. I'll use some thermal paste underneath these things and then screw them into the plate. And then underneath the plate, I've got a plan for a heatsink. So let's go ahead and I'll remove this plate. Well, I got the whole thing put back together again, at least temporarily, so you can kind of get a look at it here. Got a real nice handle. You can adjust the tension on it. You can use it as a wire stand or a stand. Got a place for a rocker switch. I kept the rocker switch that was in it, and I'm going to reuse it. It'll turn the fans on and off. Otherwise, the unit is pretty much passive. I got to put 2 sets of inputs, 2 sets of outputs for the 2 channels that'll be here. I'll give the thing a good coat of paint. I'll clean it up first. I'll make sure that I sand all of the edges smooth so I don't wind up cutting myself a little bit. And then we've got a place back here for the cord. I kept the cord as well. There's a place for a fuse. I can put a fuse holder in. They really thought of pretty much everything on this case. I love it. I love the case. All right. You'll see more later. Well, here's a little look at how it's going so far. I got the perforated metal front. I cut out the front plate to make room for the screen. And then I mounted the large heatsink on the inside. And I mounted all of the parts to the top. But in order to show you that, I'm going to have to open this case up again, which I'm going to do. So give me a couple of minutes, we'll take a look. Okay, we removed the cover and exposed at least the top shelf. And here you can see the aluminum plate that I purchased and then cut to fit. It doesn't have the well in it that the other one did. And that allowed me then to mount all of these power resistors onto the plate and into the heatsink below. Now the heatsink is attached to the plate in the center by these tapped screws, and then all of these power resistors go right into the heatsink, and each one of the holes had to be drilled and tapped, and then it gives us a nice firm connection. The last step will be I have to take all these parts off again, rub heatsink grease between the parts and the plate, and then remount them. Same thing for the heatsink underneath. The bottom side of this plate is going to have heatsink grease that'll make contact with the heatsink, and then when you squeeze it all together using the screws, that'll give you a nice thermal connection, and hopefully we can radiate the heat down through the heatsink. And then the fan, actually 2 fans, will be blowing from outside, sucking air in, blowing it across the heatsink, and exhausting it out the front to cool it. So that's the plan. Right now I'm gonna do some cleaning on the metal, getting ready for some paint. I do have a little clearance problem. Here's the heatsink, you can see it. And there's the switch hole up there. But there's these first two fins right up near the switch. I got to create a little notch in each one of them to make clearance to mount that switch in there without touching it. So I'm going to use a Dremel tool. I'm going to notch out those two fins, and while I'm at it, I'll probably get a grinding wheel, and I'll smooth out the metal around the cutout here, and probably dull the edges so it's not sharp and like a knife. And then we'll see where we go from there. Well, here we are. We've repainted the cabinet. Very beautiful blue. I've still got tape on the feet. I'll have to pull those off. And so we have a very large heatsink on the interior there. You can see the teeth of it. So we're drilled and tapped into that. So all of the heat from the resistors, or at least a lot of the heat, will be transferred into that heatsink right through the plate. And then there'll be two fans in the back, like I mentioned. I haven't got them yet. I can't finish until I get them. But I got two fans coming that'll draw air and blow it across the heatsink in both sections where those resistors are. And you can see I remounted the power switch, so that'll be nice. I'll reuse it to turn the fans on and off. It's the only thing the power is there for. So now what I got to do is I got to mount all of the input and output terminals. There'll be 8 terminals that have to go across there. I'm hoping that I get lucky enough to have plenty of room for that, but it's looking pretty good. And see you in a little while. Well, we're getting closer. This is how she's looking today. Begin to get the idea of how we're all going to turn out, but we've got our inputs and outputs for both channels. On-off switch. We painted the cover. And we've done some more. Give me a moment and we'll give you an internal look. Alright. What we've done here so far, I think I mentioned this earlier, but I've drilled and tapped all of the screw holes through the aluminum plate and into the heatsink underneath. And you can see the size of the heatsink there. She's a biggie. And then on top of that, I've got a thermal compound between the aluminum sheet and the heatsink underneath, and then under every one of these resistors, there's a layer of thermal compound as well. So hopefully we transmit the heat rapidly down to the heatsink. Then I'm working on the rear fans. I've ordered a 3-inch hole saw so I can cut the holes in this panel, and then that will mount in the back of the unit here in this area, and we'll blow the air across the resistors and across the heatsink. The on-off switch, which was on the front, the rocker switch, will turn the fans on and off. That's basically what it is. And we should be complete then at that point. I mean, I've got to do some wiring here to wire up both channels, and I've got to wire up the fans. But I'll check back with you later. Well, it's almost done. The only thing left to do is to connect the inputs and outputs, and I have to wait until I get some terminal lugs that I have on order. They should be in within the week, and I can finish it up. But everything else is done. The cabinet is beautiful. We've even labeled it. As you can see, our input 1, output 1, input 2, output 2, on, off. Got all of that done. If I turn on the switch, you can hear the roar of the cooling fans, and I can feel the draw of the air through here right now. And if I turn her around so we can take a look at the back side. Okay, we can see the back side here. I got my little Baptronics label on it. That's me. Fans are roaring. We've got our 12 volt half amp input. So we are in beautiful shape. I can't wait for those lugs to get here so I can finish this thing up. Alright, we'll get back to you. Okay, well, we completed the build of the unit. We've got it connected up to this Sansui R50. We can get 45 watts RMS a channel out of this thing. And we're going to try and use that. We've got these two General Radio 1840A output power meters, but they're only good to 20 watts without this extra unit. This unit takes 90% of the power away and provides only 10% of the power to the general radio. So the top power input into this thing is 200 watts, and if I read 20 on this, it's actually 200. So if I go to 45, which would be my peak, I'll be just between the fourth and the fifth meter indication on both units. I've also connected up a feedback electronic EW604. It's set to read 100 watts maximum, so 45 would be midway between 0.4 and 5. So we're gonna use that as a double check, and I'm gonna look at the voltage reading AC wise coming out of my my unit, which is across 8 ohms. And we're going to see what the voltage is, and we'll calculate it that way. One way or the other, we're going to determine, maybe all of them should come together and tell us that we're reading properly. So let's go ahead and turn on the power. Alright, the EW604 is giving us a reading of about 44 watts. We're getting about 45 on both of the GAs. I'm reading 18.97 volts on the Hewlett-Packard. Now if I put an 18.97 and square it and divide by 8, I get 44.98 watts, so 45 watts. Let's go ahead and turn this off so we don't overheat the unit. So it looks like it's working on both channels. And my feedback control unit, well, it was a little off. Not bad, but like a watt. So I'll have to look into that. It is a little bit touchy on the calibration, so maybe that's what it is. I need to clean that pot. But man, I am happy. It's working like a charm. You can hear it roaring. It's actually quite cold. So there really hasn't been any overheating or anything yet. And I can turn the unit off. You can hear the fans go off. There we are. Thanks for watching.